Hello and welcome to the second of Bakul Talks about the Nobel Prizes of 2020. I'm speaking here from the Bakul Library in Satyanagar, Bhubaneswar, where it's a public library which has been set up entirely with public contributions. You know, a real public library in that sense, by the public, for the public, and of the public. So every book that you see here has been donated by individuals like you. People who thought that their books should be used by others as well. And everyone volunteers here. It's basically a movement Bakul is basically a movement to demonstrate the power of volunteerism. And when this pandemic happened and the libraries closed, all the activities that we used to have at the library, like book launches, storytelling sessions for children, other meet the authors and other public lectures, that stopped. And so we kind of reinvented ourselves and went digital. We started with storytelling sessions for children, and even now, every Saturday, we travel to different countries on the planet, virtually, of course, with one of the finest professional storytellers from that country. Last Saturday, we went to Mexico, and we were a part of the Day of the Dead festival. So we're trying to give as much multicultural exposure, as rich an exposure as possible. So if you would like to see these sessions, they're available on YouTube on the same channel where you're watching this, Bakul Foundation channel on YouTube, or the Bakul Foundation page on Facebook. In the video section, you can find the previous sessions. The coming Saturday, we are traveling to Brazil. Every Sunday, we have storytelling in Odia, again, which is live. So both the sessions on Saturday and Sunday, it goes at 9 p.m. on Twitter, Facebook, and YouTube, live on all these platforms at 9 p.m. And the videos can be watched later as well. And then we started Bakul Talks, because the storytelling sessions were, of course, for younger children. And this, though it is for everyone, our focus segment is young people. And we wanted public lectures. And because we felt, something that was happening earlier and is not as much happening now, is lectures by experts, which can actually stimulate the thinking of people irrespective of what they are studying currently. Our education is very fragmented these days. So if I'm a student of literature, I know very little about what is happening in the world of science. But we all know that the Nobel Prizes are given for research which has contributed the greatest benefit to mankind. It has impacted the lives of all of us. So in a way, when we talked to our young volunteers, and many of them said, yes, we were curious to know why the Nobel Prize was given. We know instinctively that it's a very significant work, but somewhere we feel that maybe it is beyond the reach of our comprehension, or, we won't really make that effort. And this is where the Bakul Talks and this series comes in. And when we started Bakul Talks, we were very clear about one thing, that we will take up topics in Bakul Talks which are of common interest to any curious individual. You need to be curious, of course, and otherwise these talks are not for you. But it is irrespective of whether you are a student of science, or a student of arts, or a student of engineering, or whatever, law, whatever your disciplinary persuasion might be, this would be of common interest to any curious individual. And this would be interesting and intelligible to teenagers. That is our focus. That teenagers should be able to understand it. Or in other words, any common person should be able to understand it. But it should be insightful for intellectuals as well. It is not just, so Bakul Talks will not be only stuff that is good enough for young people. These are talks on subjects that are good enough for everyone, for any adult also. And that is why we started Bakul Talks with a series on the Nobel Prizes of 2020, which were announced in the month of October. And soon enough, we started this. And we've been lucky to have a wonderful panel of speakers. The first talk was on the Nobel Peace Prize last Tuesday. So Bakul Talks is every Tuesday, and it'll run through the month of November. The last talk is on December 1st. There are 6 Nobel Prizes. We started the last Tuesday. Today, we are talking about the Physics Prize, and the last one will be on 1st December. So the last one was on Peace Prize, and we had Mr. Parajoli, who is the country director of the World Food Program, which won the Nobel Peace Prize. I mean, we can't have a better person than him for that. So similarly today, the research that was rewarded, that was awarded the Nobel Prize in physics, 3 people got it, and all 3 of them they got for their research on black holes and cosmology. So the speaker that we have is a very eminent professor of physics and a cosmologist himself, Prof L P Singh, whose primary area of research has been black holes as well. So you have the best person, and not only that, he is someone, unlike a lot of scientists, they may not be good communicators to a general audience, or they may not make much efforts to reach out to young people. But Professor Singh has been doing that. He has in fact authored, he is from Orissa and we are very proud of that, and he has authored 10 books in Odia meant for young people. So we could not think of a better person than him to introduce the Nobel Prize winning work. It is not so much about the prize winners we'll be discussing, but about the ideas, what is their contribution in the world of science and for larger understanding of the universe and mankind. The next talk will be on the economics prize. And again, we have a wonderful speaker, Professor Jeevan Rampal from IIM Ahmedabad, Indian Institute of Management, Ahmedabad. Again, we have not got him just because he is from IIMA, but also because he's an authority on auction theory, for which the Nobel Prize this year was given. So we have a wonderful panel of speakers. Every prize is being explained by one of the best persons in the country. So I hope all of you will be joining us every Tuesday at 7 p.m. here on YouTube, on Facebook, and on Instagram. I'm sorry, last time there was a problem with Instagram, but we have sorted that out and we'll be live each time. Just before we start with today's talk, I just want to update you also on something, because as I said, Bakul is a movement for volunteerism. And when we started our digital engagement, and we realized that there is a problem in digital learning. It is only so many people who can access it. I mean, for example, research says that more than 56% of children in India do not have access to smartphone. So those of you who are attending this session are able to do it because you have a digital device. You have a smartphone, or you have a laptop or a tablet by which you are able to access this. But imagine children who don't have a smartphone. Now, with schools being closed, the only learning that happens now, even for children in government schools, even for children in villages, is online. But then they don't have a smartphone. So we felt it was our responsibility, as we were working in the space of digital learning, that we should help children as much as we can. So we started a campaign called Donate Smartphone. We asked people to donate any used smartphone which is usable, but they can give away, to give to us, so that we have identified children who need it and we will give them. Unfortunately, not too many used smartphones came because people don't have. They've either given it away or exchanged it. But then we sought contributions. So now people, and I'm very happy that many people have contributed. And you can contribute as little as 100 rupees, as much as 10,000 rupees. Some people, of course, have contributed even over 20,000. So there's a site called giving.bakul.org. You can go to this link and you'll find the address. If you have a smartphone to donate and use that smartphone, you can do that. You can buy a new smartphone and give it, or you can contribute to buy smartphones from as little as 100 rupees to as much as you can. We had the first major contribution last week. There's Wisdom Tree Global School in Bhubaneswar. They donated a set of 10 phones to us. And so this is the giving of the phones. Next, let's go fast. Yeah, and these phones we then gave away at, in Bhubaneswar, there's a Madhurmai Ashram. Now, Madhurmai Ashram is in the premises of the jail, the main jail in Jharpada, in which the convicts are kept. And these children are children of whose parents are in prison. But these children stay in this shelter home, in this ashram, and they go to regular schools. And there were only about 3 phones of the caregivers, for all the children that were there. And we gave away our first set of phones there. So that, there are around 50 children and they had only 3 phones. So we have given them the first set of 6 phones now, so that at least children belonging to a particular class can, have some learning through at least one phone, shared learning. So this is something that will be continuing. So if any of you would like to contribute, as I said, please visit our site, giving.bakul.org, and you can contribute through that. So thank you very much. I won't take more of your time. Now we'll have Professor L P Singh, who will talk about the Nobel Prize in Physics 2020. And the Nobel Prize in Physics is very interesting this year because it was given for research on black holes. Now, Roger Penrose, who now many of you would know that Albert Einstein, probably the most famous scientist of the 20th century, he was given a Nobel Prize, but not for his famous theory of relativity. And apparently, I'm not a physicist, from what I read, apparently he was not given the prize because the theory of relativity was not proven. Now, Roger Penrose, who got the Nobel this year, apparently proved the existence of the theory of relativity. Now, we'll know more about that. Now, how did he prove that? We will know that. Similarly, many of you would have heard of Roger Penrose's more famous collaborator, Stephen Hawking. In fact, they used to do a lot of work together. They have co-authored books, one of which is in the library at the Bakul library also, which I'll show you later. But we'll talk more about that later. Professor Singh now to explain the significance of the research that got the Nobel Prize in Physics this year. So please.
Thank you so much for a beautiful introduction, which I may not be able to live up to. So let me first thank with a profuse thanks to Bakul and the co-volunteers for giving me this opportunity of talking to people on the Nobel Physics Prize of this year. Before I do that, let me also extend my heartfelt thanks to Bakul, just to remind them of the fact that 10 years back, we in the region where we live in Bhubaneswar got some saplings from Bakul Foundation, which I would now report back have grown to tall trees and are providing shade to the passers-by in the hot noon. They're also sporting flowers of various hues in their chosen seasons. They're also providing homes to many birds of many different feathers, and most importantly, they're also giving oxygen to the atmosphere and making the life of every human being more comfortable and atmosphere more refreshing. So with these few words of my thankfulness, let me now move on to the Nobel Prize in Physics for this year. Nobel Prize is the most prestigious prize awarded in the fields like literature, physics, chemistry, medicine, peace, and economics. Economics was actually added later on in 1969. But to start with, it was 5 prizes: peace, literature, physics, chemistry, and medicine. As you know, this prize is named after Alfred Nobel, who in fact bequeathed most of his wealth, something like 30 million Swiss kroners in the year 1896 to Nobel Foundation to make arrangements for awards for those people whose work have actually brought greatest benefit to humankind. Now, following that ideal, because he was an industrialist, a chemist, an inventor, and he had something like 355 patents to his name. So he earned a lot of wealth, particularly through explosives like dynamite. And so following the lines or the wishes of his will, actually Nobel Foundation has been awarding these awards since 1901, from the break of last century. So this year's physics prize has actually gone to black holes. So these are basically black hole prizes. And half of the prize money, which is around 8.5 crores in Indian rupees, would go to Roger Penrose, for discovering that the formation of black holes is a robust prediction of general theory of relativity of Einstein. The other half would be equally said by Reinhard Genzel and Andrea Ghez for, in fact, discovering that there is a compact object in the center of our galaxy. So, as you can see, one of the prize, one section of the prize actually goes to basically proving something using mathematics. The other half actually goes to two people who have performed experiments, who have made immaculate observations over many, many years. And in fact, I would like to emphasize, since there are young friends around who are possible future Nobel laureates, so in fact, it is mathematics and experiment which go together and make science somewhat different from humanities. Here, mathematics is completely relied upon if you really want to do theoretical physics. And as you all know, without experiments, without observations, science is also lame. So therefore, these are the two strong pillars on which science actually stands, and these are the two things which basically make science universal. So you can see that the principles of science hold everywhere, and they are also verifiable everywhere, everywhere, whenever one performs experiments in the similar conditions. So with these words, let me tell you that Roger Penrose's work actually is a work on general theory of relativity. And he is discovering basically that black hole solution is a robust prediction of general theory of relativity. Now let me tell you that general theory of relativity of Einstein is basically a relativistic theory of gravitation. So it is basically theory of gravitation. Now, as far as we know that the theories of gravitation were more or less brought to the realm of science by no less a person than Sir Isaac Newton in the late decades of 17th century. With the publication of Principia Mathematica, he actually showed that gravity is a universal force and it exists everywhere wherever there is mass. And his famous equation, can I have the first slide, please? Can I have the first slide, please? Hello? Yes, this equation is known to almost all school students, that the force between two masses, M1 and M2, goes like 1 over r square, where r is the distance between them, and g is a constant of proportionality, which now we call Newton's gravitational constant. Okay, thank you very much. So this is how we understood gravity. And this theory, believe it or not, had a rule for 230 years. As George Bernard Shaw has said somewhere, that the kings and the emperors actually have their empires for 50 years, 40 years, 30 years, 100 years. But these are the people, for example, the rule of gravitation by Newton ruled for 230 years and even rules now if you are in the right regime. I'll just explain that to you. And this equation, in fact, is the key equation which he used to describe the Kepler's laws of planetary motion, the motion of the planets around the sun in our solar system, which is nearby. Okay, so in fact, he invented also a branch of mathematics, which we know as the differential calculus, along with Leibniz in Germany independently, to in fact prove the Kepler's laws mathematically, using this law of gravitation that I just showed. So therefore, you can see how important mathematics is for doing science. That's very important. One should not actually make light of it, because without mathematics, science really cannot stand. So this, in fact, was the story till Albert Einstein actually appeared on the scene in the early years of 20th century. In 1905, as you all know, which is called the year of miracle, he published 3 papers. One paper was on photoelectric effect, one paper was on Brownian motion, and the other one was on special theory of relativity. And now special theory of relativity is unique in many ways, because here comes a man who tells us for the first time that our physical world is actually not three-dimensional as we view it, and with time as an independent dimension. That's not the story. In fact, he for the first time told us that our physical world, in fact, is a 4-dimensional world. It's a space-time world. It's not space and time, it is space hyphen time. So, and then he extended his, then you know that he also derived E is equal to mc square and many other things from that mass variation with velocity, time dilation, length contraction, that I'm not going into. But he for the first time showed that this universe is 4-dimensional, where space and time are intimately related to each other. Now, then 10 years after, he actually generalized his special theory of relativity to general theory of relativity, where he also took acceleration into account. In this special theory of relativity, there was no place for acceleration. He did not consider that. The 2 frames of references were moving with uniform velocity. But then in general theory of relativity, he came up with another unique imaginative idea that gravity, in fact, is a result of the curvature of space-time. The space-time that he introduced 10 years before, if there is a curvature there, then the force of gravity appears. And what causes this curvature of space-time? It is the matter that causes curvature of space-time. The more matter you have in a particular place, the more curved space-time actually become. And then this is the basically content of the Einstein's field equations or the equations of general theory of relativity. Can I have the second slide, please? Yes, this is in fact the Einstein's field equation. So the terms which actually appear on the left-hand side of this equation, they all correspond to curvature of space-time. On the right-hand side, we have a quantity. This is a tensor equation. I would not like to take much time in bothering you with tensors, etc. But I can only tell you that scalars are quantities which preserve their values everywhere in all frames of reference. But vectors can change their values because they have components. They now develop components. Just as you have read in +2 or even high schools nowadays, that vectors have a direction. So that means as you change your directions, the values change. So therefore, their directional dependency arises, and that is taken care of by indices in mathematics. And there you have just one index. Let's say X component or Y component or Z component, like that. But here you have 2 indices like mu nu, and mu nu actually refers to space-time that I was just talking about minutes before. So mu and nu, each of them take 4 values, 3 space values and 1 time values. So therefore, they are actually tensor equation, more complicated in nature, but people call this as the most beautiful equation of physics. Why? Because the left-hand side is basically the curvature of space-time. The right-hand side tells us what kind of matter and energy is present in this space-time. So therefore, one nice way of explaining this equation is, so matter tells space-time how to curve, and space-time tells matter how to move. So Thank you so much. Yes. So this equation was an enigmatic equation in many ways, because here for the first time you see that matter actually causes curvature of space-time. It's a beautiful imaginative idea. In fact, maybe because of such effusion of creativity in that mind, Albert Einstein's, he was in fact adjudged as the man of last century, 20th century, beating Mohandas Karamchand Gandhi to second place. In any case, so it's a unimaginably creative thought. And then you have to, as in science, as I told you minutes before in the beginning, that everything that you think has to conform to experiments. So he had predictions, and those predictions were remarkably verified, particularly the bending of light near sun. So therefore, people had to wait for a total solar eclipse. In 1919, an experiment was performed by no less a person than Eddington and his collaborators in South Africa. In a total solar eclipse day, they measured how much actually the light of stars coming by the sun are bending, and they found this bending to be in exact agreement with the calculation of Albert Einstein. If you do the same calculation with Newton's laws, it should have been half. So there actually Einstein wins over Newton's prediction, Newton's theory, and he immediately becomes a genius. And so this equation therefore governs now the all phenomena of gravity, whether it's a low gravity situation or a high gravity situation, whether the gravitational force is small or large. This equation has answers to everything until date. Even after 100 years of its appearance, there has been no experiment which actually has falsified Einstein's field equations predictions. So just 2 months, less than 2 months of writing this equation, the first solution to this equation was written. Now, when I say solution to this equation, what I really mean is that the solution actually appears as the structure of the space-time, which we call in mathematical term a metric. Because this R mu nu, etc., which I just showed to appear in the left-hand side of Einstein's field equation, they are arising from the curvature of space-time. And how the space-time is curved is all given by what is known as a metric, which is a tensor. So G mu nu, which was also appearing in that equation. So if you know what the G mu nu is, you know what your space-time is like. So use that kind of solution to this R mu nu minus half G mu nu equal to 8 pi G T mu nu. This equation was immediately written down by Schwarzschild. Schwarzschild, in fact, was a mathematician, astronomer of Germany. He was working in the war front, but even with that kind of engagement in a war front, he worked in the nights, and within 2 months of Einstein's equation being written out, he actually provided the first solution for it in terms of G mu nu. And that Schwarzschild solution, in fact, captivated the minds of people who worked on gravity almost till date. People are, because why? Because that solution, in fact, had seemed to have two singularities. Singularities means in mathematics, we mean that if something blows up, becomes infinite, then we say that we have singularities. So there, in fact, people found that some components of this metric, because as I told you, metric, in fact, gives full information about the structure of space-time. And if some components of that metric tensor actually becomes infinite, then we know that there is some problem which we have to explain. Because in physics, just in our day-to-day life, we don't actually deal with infinities. Finite things are all right because we can make sense out of it. But when we encounter infinities in the calculation, then we know that something is either going wrong or there is something very interesting which we don't understand. And in fact, to our good luck, it is the later one which was actually happening in case of Schwarzschild metric. So when the queries actually went on, people off and on started working on these solutions. Then they came to understand that if you have that, in fact, that metric was written when you have a mass concentration in some place and outside you have vacuum. So only some mass is present. And then it was found that a radius, which is now known as Schwarzschild radius, if the mass is very concentrated, and you can calculate, there are 2 points at which actually the infinities occur. One is at the center of the mass point, r equal to 0 in that equation, and then at a surface which is actually enclosing that mass. So the surface which encloses that mass was later recognized and called Schwarzschild radius. And what happened actually is that once anything, matter or light, that crosses that boundary of that surface, they can never come out. So that was the first hint of something very strange happening. So that was like a black hole, because why it cannot come out, why matter cannot come out, why light cannot come out, because the escape velocity that you read in plus 2, for example, the Newton's equation itself suggested that if you throw a stone into atmosphere, you know that it, depending on what force you give it, it would return to the surface of the earth. But if you give it a sufficient velocity, then there is a possibility that the stone would never return back to the surface of the earth. So that velocity is called escape velocity. It escapes the gravitational pull of the earth. Now, if this velocity happens to be equal to the velocity of light in vacuum, which is the ultimate velocity that a material particle can attain, which was shown to us by Einstein in his special theory relativity in 1905, then that thing would never come back, because even light cannot come back. So no other material particle can come back. So therefore, it was calculated from Schwarzschild metric that if a distance like Schwarzschild radius, where the escape velocity actually becomes equal to c. So since nothing can, or greater than c. So therefore, since nothing can become actually greater than c or equal to c, excepting photons, so nothing can actually escape these surfaces, and therefore anything that is hidden behind that surface is called a black hole, because nothing, not even light, can escape from those surfaces. So that is how the idea of black hole was born. But there were many approximations. Mathematically, there were many approximations which were made, and people did not, even Einstein did not believe that such a thing would ever exist in nature, would be a reality. Because what you get in mathematics need not be there reflected in nature. So therefore, time passed on, and there were many important works. Just after a few months of Einstein's death, actually there was a very seminal work by Amal Kumar Raichaudhuri of Calcutta, where he actually showed that if you have a flow of lines, you think of, since we were now thinking of the entire universe using the Einstein's field equations, because the entire universe, I should also tell you, is governed, the large scale structure of the universe, the solar system, the galaxies, the clusters of galaxies, superclusters of galaxies, they are all governed by only one force, that is force of gravity. So therefore, there is only one equation that should apply, that's the Einstein's field equation there. Talking about Nobel Prizes, for example, you see this Peace Prize, Literature Prize, Economics Prize, they all pertain to human beings, our societies. Now, you will also listen to Nobel Prizes in medicine and chemistry, where you will see that they are working at a very minute level, at nanometer scales, with DNA molecules with genes, etc. Here, for the as a change, we are now talking about scales which are much, much bigger, millions and billions of kilometers, because we are now talking in terms of astrophysics. So the black holes, therefore, could be a region of space-time from which nothing can escape. Now the question was, would such kind of space-time would really exist in nature or not? That's the big question. And as I said, Kamal Raichaudhuri showed that because of gravity, if you have actually flow lines, then and certain other conditions are satisfied, like positivity of energy, etc., then in fact these flow lines would converge. They would never diverge. So once they converges, they would probably converge to a point, obviously. And so therefore this kind of research was taken up 10 years after by Penrose, and he proved that irrespective of the symmetry of the physical system, these lines, even light-like lines, once they cross the event horizon, the Schwarzschild radius defines actually the event horizon. So once they cross the event horizon, they would in fact all would converge gradually to a singularity, where the curvature scalar, whatever you calculate, would blow up, or in other words, we sometimes say that the laws of physics would cease there. We would not be able to apply laws of physics anymore. So this is therefore the biggest contribution of Roger Penrose. So therefore some studies showed that some stars with certain conditions, like if these stars are born with a mass something like more than 20 times the mass of the sun, they are bound to die as black holes. So as we all know, let me just say in few words, that we know that stars are actually fusion reactors. In sun, for example, the hydrogen nucleus, 4 of them, are incessantly fusing to produce helium nucleus. And because of this fusion, we get energy. And that energy, through various processes, actually comes out as heat and light to us. And that is what actually makes entire life possible on the surface of the earth. So we are very lucky to be at the right distance from the sun, to have the right mass for the earth to sustain an atmosphere of 100 kilometers above us. So there are many things that actually is happening, which is a gift of nature, and that is what is making possible life on the surface of the earth. But so therefore, if and Chandrasekhar proved in early 30s that stars like sun would actually die as white dwarf. He got a limit, which is today known as Chandrasekhar limit of 1.4 solar mass. So the white dwarfs cannot have masses more than that. Similarly, if the star is having, when it is born, when it is taking its birth, if the mass of the star is around 20 times the mass of the sun and more, then they are bound to die as black holes. Because these kind of fusion processes, they actually continue for stars of different masses, they would continue up to the fusion of iron nuclei, because iron are the most stable nucleus we have, and then there would be no fusion process actually to sustain the gravitational pull, and gravitation would eventually cross the matter to very high density, and eventually it would become a black hole. So therefore, he in fact showed that some stars would certainly become a black hole. And you might have seen, can I see the next slide, please? So last year, on the 10th of April, 2019, actually all the newspapers of the world carried this picture of a black hole. This black hole is actually not in our galaxy. It's in the M87 galaxy in the Sagittarius constellation. So that is why it is called SGR, a star. Star means some exciting object. So it's an excited state. Okay, thank you. So therefore, we now see a robust experimental proof of what actually Roger Penrose concluded by his study of Einstein's field equations. So I think it's the Nobel Prize which has gone to him is worth it. Now next, I move on to the other two prize winners. One is Reinhard Genzel, who is now the director of Max Planck Institute of Extraterrestrial Physics in Ghez, and Andrea Ghez, who is now a professor in University of California, Los Angeles. Professor Reinhard Genzel also holds emeritus professorship in University of California, Berkeley. So what these people have done, they have actually been able to point out to us that there is in fact a very compact object in the center of our galaxy, Milky Way. Now this story began once again very early years of 20th century. People from 1930s through 50s and 60s came to know that there are very prominent sources of radio emission in our universe. Now, first of all, people thought that they could be from from objects within our galaxy, because first of all, we did not know that there are galaxies beyond our galaxy. We even did not know that there are things beyond our solar system. But then things actually proceeded very fast after Einstein's equation were written out, because that was immediately applied to study cosmology, and the astrophysics, in fact, proceeded very fast. And then 1929, Hubble, in fact, told us that there are galaxies beyond our galaxies, and he measured with what velocity actually these galaxies are receding from us. Therefore, he more or less proved experimentally that our universe is an expanding universe. And then there was this Big Bang theory in 1948, 50s, let's say, in the middle of last century. And then the microwave background radiation was discovered, which actually gave credence to the Big Bang theory of creation of the universe. And so it continued with the universe. But so far as the astrophysics is concerned, so far as the physics of stars are concerned, then these are a very intense source of radio waves were actually seen from early 30s. They were studied in 50s, 60s, and in 70s, actually Lyndon Bell and Martin Rees, they in fact said that these intense source of radio waves, which people have been calling as quasars, quasi-stars, or quasi-stellar objects, quasars, are in fact the centers of various galaxies. So gradually it emerged that at the center of every galaxy, there is an active nuclei. And this active nuclei, in fact, hides a black hole within it. That was so that actually, that notion gained popularity, and people started studying it. And with the proof of existence of black holes, this also became still more urgent. And then there were black hole solutions, apart from Schwarzschild solutions like Kerr solutions, Neumann solutions, etc. in the early 60s of last century. So therefore, the opinion gained, people actually more or less became very confident that yes, there are perhaps very energetic sources at the center of every galaxy, just as we have a nucleus at the center of an atom, or just as we have a sun at the center of the solar system. So now these two groups, led by Reinhard Genzel and Andrea Ghez, they actually used the largest telescopes to view the black holes in the Virgo cluster, M87 galaxy of the Virgo cluster. M is Messier, the man who actually catalogued the galaxies. So M87 means this galaxy actually had the 87th position in the catalogue of Messier. So there, they were able to, in fact, find, in fact, I had just showed you the picture of that. So they wanted to see whether there is a similar supermassive black hole at the center of our galaxy or not. That's the question. So they started their observation from 1992 or early 90s, and then in 2008, they actually declared the result that yes, we have become confident to declare that there is a very massive compact object. Massive means the mass is of the order of 4 times, 4 million times, 4 million times the mass of the sun at the center of Milky Way. There are many difficulties actually you get when you observe such things. First of all, they used the best of the telescopes that were available, and then these telescopes also have to be sort of new technology and a new technique have to be applied, because there are lots of interstellar dust, because they are not very close to us. We are on the surface of the earth, and these telescopes are actually placed on the surface of the earth. One is in Chile, another is in Hawaii. So the one used by Reinhard, Professor Reinhard Genzel, is in Chile. That is the telescope of European Southern Laboratory, ESO. And the telescope used by Andrea Ghez is actually in Hawaii. That's of the Keck Laboratory. So these telescopes are actually terrestrial based. And we are more or less something like 2,600 light years away from the center of our galaxy. And so therefore, and in between a lot of interstellar dust and various kind of turbulence, even our atmosphere also obstructs the clear image of these things. So it has to take long, long years, and it has taken. And fortunately, however, they were fortunate to see that there are some stars which are moving around this compact object in closed orbits, and particularly S2, which is a star, takes only 16 years to complete one orbit around that compact object. So therefore, observation of this complete orbit, as well as, so you have to calculate many things. First of all, what is the orbital velocity, whether it's really going like 1 over r to the power half or not. You have to use again mathematics there, because otherwise it could be any collection of massive objects inside that around which the star might be moving. You have to prove that actually there is one compact object which is at the center around which the stars are moving. And for that, you have to correct your, you have to increase your resolution first of all, so that you pinpoint over the stars which are very close to that compact object. Then you study their orbital motion, find out whether they conform to the rules that, for example, the planets in the solar system are conforming to when they are going around the sun. So all these have to be put in place. And then in 2008, both the groups showed that, yes, they are now confident that they have found, they have discovered one compact object at the center of our galaxy whose mass is around 4.5 times 4.5 times 4.5 million times the mass of the sun. So you see, the mass is 4.5 million times the mass of the sun. So we are talking of very big masses. We are also talking of very big distances, like as I said, 2,600 light years. And so these are all big objects. So, and finally, however, it was miraculous that they could see the complete orbits of these stars. Can I see this last slide, please? So that you can see how beautifully they have been able to obtain the orbits of the stars. You can see that. How beautifully the orbits of the stars which are moving round. So they are all moving within about one particular common object, and that the location of that common object is the compact object which they have really discovered which eventually we will see. We will have more picture. We don't have a real picture of the black hole there, but we are now certain that there is a compact object, and that must be the Sagittarius A star supermassive black hole, which is sitting at the center of our galaxy. Okay, so thank you so much. Thanks. Okay, so therefore, you can see all these people through their ingenuity in mathematics as well as in experimental technique and technology have invented or discovered, confirmed the existence of black holes. And these are very interesting. Now you might ask, in what way have they conferred the greatest benefit to the mankind? Okay, the other day you were listening to a Nobel Prize talks on food programs for peace. So that's true. As long as man is hungry, he or she cannot really think of other ideas. Literature, science, and all other fine arts would probably take a back seat. But if you have enough to eat, then there is also a hunger of mind to know, to learn, and to grow. In fact, that is what civilization really means. So therefore, these discoveries actually satisfy the human curiosity, which Sujit was talking about in the very beginning. So man is curious. As soon as the belly gets filled, he or she is curious. They would like to know who we are, how we live, what we are, where are we living, what is our surrounding, can we explore it? Yes, the answer is yes. That is, once you do that, you actually also confer a great benefit to the humankind in its progress and to the progress of civilization. So I would like to stop here and open it for discussions.
Thank you very much, sir. In fact, I just wonder, I studied literature, but if I had heard one of this talk of yours when I was about to decide whether to continue in science or not, I don't know if I would have chosen poetry over physics. Maybe I would have gone for physics. So we never know what would have happened. But this was just what we kind of had hoped for, and I knew that this is going to happen. And I very much liked, as a student of literature also, and we had all these questions about, why Einstein did not get the Nobel for relativity, something that I flagged off earlier. So there was something that I understood from this, and I want you to clarify whether my understanding is correct. So you talked about two major pillars of physics, and in fact of science. One is mathematics, and the other is direct observation, verifiability. And what I understood is, now Einstein's theory of relativity was at the realm of theory, mathematics, but it had not been verified through observation. And so one question that I have is, now we know that of all the, and it is very interesting that you gave an entire history to the idea as it developed from Newton, from Newton's gravitational theory to Einstein, to Roger Penrose, Chandrasekhar, all of them. Now, is it because of the recent discoveries, the observation by Andrea Ghez and Reinhard Genzel, which is much more recent? Is it the fact that they could observe and prove that it has to be the black hole is the only possible explanation that made it possible to give the prize to Roger Penrose also, and for this work which had not been given the Nobel Prize so far?
So, see, many people have actually got...
it would have been possible without these observations.
Yeah. It might not have gone to these people, but you see, if you just think of Einstein's work, he did in 1905 3 works, which I just mentioned. Photoelectric effect was the work that was easily understood by people, and that was also sufficiently revolutionary in those days, because he was saying that the electromagnetic wave has particle nature, which again Newton also thought of, but did not think of this as the source of interference, diffraction, etc., which are little more physical, physics terminologies. So Einstein, for the first time, again, more or less established that the electromagnetic wave has a corpuscular nature, have a particle nature, and therefore they are giving rise to photoelectric effect, which was an experimentally verified thing beforehand. So therefore they had no problem in awarding a Nobel Prize to him. But when he talked about space and time being unified and our universe is four-dimensional, that somehow was people were very amazed. Somehow people did not really think that this might be in the realm of reality. So they probably thought that this is a good guess, but may not be correct. So therefore, otherwise, you see, as soon as the general theory of relativity was verified in the low gravity situation, like bending up light coming from distant stars across the sun in 1919, and as time dilation was also verified, the precession of the perihelion of Mercury planet was verified. He was given Nobel Prize, but he was not given Nobel Prize on relativity, mostly because I think, I may be wrong, but because people really did not think that such ideas could be real. They were really revolutionary.
And as you said, Roger Penrose's work in a way proved,
Many people, all tests have actually proved him correct, because you see, gravitational wave Nobel Prize in 2017 to physics is another vindication of his field equations. So whatever tests have been done so far, in fact, the Big Bang cosmology model is also a vindication of his. So the universe is expanding. There is a microwave background radiation present in the entire universe of the temperature of 2.7 degree Kelvin. That is also a result of Einstein's equation. So everything, in fact, is flowing from Einstein's equation, and a lot of prizes have actually gone to those results.
Thank you very much. Of course, before I forget to say, those of you who are watching it on Instagram, we're going to end now on Instagram because we have a duration of 1 hour only. We will continue on the other platforms on YouTube and Facebook. But whoever is watching us on Instagram or YouTube or Facebook, please do not forget to subscribe to the channel on YouTube or to like the page on Facebook and to follow us on Instagram, so that you keep getting the updates and you get to know about the other talks in the series. But then, as I said earlier also, every Tuesday this month till 1st of December, we will be coming back to talk about another Nobel Prize with an equally wonderful expert like Professor Singh today. We will take some questions now, but I love the fact that Professor Singh addressed at the very beginning to the potential Nobel laureates. That is our dream, actually. And I was doing some background reading, and I realized that, of course, Professor Singh talked about Dr. Chandrasekhar, who was an Indian who got the Nobel Prize for physics. But before that, I don't know how many of you know, for me, it was a discovery that C.V. Raman, when he got the Nobel Prize in 1930, he was actually the first person from Asia to get a Nobel Prize in any of the sciences. Before that, it had been mostly Europeans who were getting it. In fact, there was an American who got the Nobel Prize for physics before that, and C.V. Raman then got it. But then C.V. Raman...
Can I just say about C.V. Raman, that's very interesting. Students should know that actually he was working in Indian Finance Service. When he was going by tram to his office, he actually saw the signboard of Indian Association for Cultivation of Science, from where he had picked up Professor Das to talk about the Nobel Prize in Chemistry. In fact, that was perhaps modern physics actually modern science, in fact, came to India through Calcutta. So it was Dr. Mandralal Sarkar and Asutosh Mukherjee and all those elites of Bengal who actually created this institution for the study of fundamental science. And it was, in fact, by chance that Raman actually saw the signboard and then saw that this room is always closed. What kind of science is being cultivated there? So he once knocked at the door and somebody came out and he said, yes, what is your problem? Then Raman said that I am such and such person. I am interested in science. I have been doing also research earlier. I have published papers. I would like to do some science. Why is it always closed? Then he said, as we understand, he took him to the nephew of Mahendralal Sarkar, who was alive then. And when he heard the whole story from Raman, he started sort of ears flew down from his eyes, and he was so happy that he embraced Raman and said, this entire building is yours from now. So you see, and then, yes, and he discovered Raman effect on the 28th of 28th February 1928, which we observe as National Science Day. And in 1930, he got the Nobel Prize. So that was the first Nobel Prize in science in Asia. And I should also emphasize, you see, S. Chandrasekhar, who got Nobel Prize later, after he did the work in 1930s, got the Nobel Prize in 1980s. So 50 years after his work. And both of them, Raman and Chandrasekhar, Chandrasekhar is actually the nephew of C.V. Raman, the son of elder brother of C.V. Raman. So Nobel Prize actually rests in genes. So if you develop an atmosphere in the family or in the society, Nobel Prizes would flow.
It sounds like the Curie family of India. Like
Yes,
Mary Curie, Pierre Curie, her daughter, son-in-law, all of them got Nobel Prizes.
That's right.
And I would like to add, in fact, very good that Professor Singh mentioned the Indian Association for the Cultivation of Science. In fact, as he mentioned, Professor Jyotirmay Das, our speaker on the Chemistry Nobel Prize, is associated with that center with which C.V. Raman was associated. And a very interesting case of accidents, happy accidents in the world of knowledge, what you mentioned. You know, that he saw this because he had joined. And so Professor Jyotirmay Das has also got the Bhatnagar Award, which is a very prestigious award in India for science, and she will be our speaker. But the other point that I wanted to add also is, now C.V. Raman's first, Professor Singh mentioned, he had already publications. He was working as an assistant auditor general or accountant general in the AG office, but he had already publications. And his first publication in a prestigious journal was at the age of 18, when he was just an undergrad student at Presidency College, Chennai. So many of you must be 18 or around that age. So we never know. As Professor Singh said, you know, there might be a Nobel laureate in you. And also very interesting a point that he mentioned, that if you see C.V. Raman's work, the discovery happened in 1928, the day which is celebrated as the National Science Day. And he got the Nobel Prize in 1930, when there was a bias against non-Europeans. There was only one non-European, an American, who had got the Nobel Prize in physics then, no one from Asia. So it was a big thing. But then just imagine, for Chandrasekhar, it took 50 years for that work to get that recognition.
That's right.
But on that, let us go to the questions that people have. Let me just see. So Manoj Kumar sir is asking, is Newton's law of gravitation consistent near the black hole?
Is what? Is?
Manoj is asking, is Newton's law of gravitation consistent near the black hole? I think in some way you've answered it, but you can...
No, it's not. It's not. Let me just clarify. Newton's theory of gravity is a non-relativistic equation. So in any relativistic situation, it would not apply.
Okay. I think Gitanjali is asking, maybe she's a young girl, so she is asking that she was not able to understand the Einstein field equation very well. So maybe a little elaboration of that.
Well, I showed you the equation, and I just explained that the left-hand side of that equation, this R mu nu, there are, can you show that slide once again?
Can you see that equation again? But till then, sir, can we answer another question?
Yeah. Okay.
Oh no, he's come. It's come.
Yes. So let me explain the left-hand side. This quantity R mu nu, or a capital R, they are actually objects which are calculated from G mu nu. There is a term called G mu nu, so you can see it, and that G mu nu is the metric of the space-time. So that determines, when you look at, it's a matrix form. It's a 4 by 4 matrix. So every term you have to look at, and if they depend on the coordinates, like x, y, z, and t, then you know that there is a curvature in the space-time. So therefore, left-hand side is completely a description of the curvature of space-time. The right-hand side, 8 pi g divided by c square, they are constants, you can forget about them. But T mu nu, which is the tensor on the right-hand side, actually is the energy momentum tensor. So depending on the matter that is filling the universe, you will get your T mu nu. If it is completely empty, then T mu nu is 0. So therefore, what I said is that this equation tells us that the matter in the space-time basically governs how the space-time will curve. Or in other words, space-time will also tell matter how to move. So therefore, if the space-time is curved, it's like a road. Space-time is curved means everything is actually moving in space-time. So supposing I'm going to my friend's house, and if the road is zigzag, obviously I take a zigzag road. If the road is straight, I take a straight road. So if space-time is curved, like the surface of the earth, let us say, then obviously light even will also take a curved path along with other material particles. And those paths are also called geodesics, which are equivalent of straight lines in the planar surfaces. In plane surface, actually we know the shortest distance between 2 points is a straight line. But in a curved surface, like the surface of a football, actually the shortest distance between 2 points is not a straight line. It's a curved line. And that curved line is called a geodesic. And so therefore, it is curvature which basically tells matter how to move, and matter tells space-time how to curve. That is basically all I can say at this moment about the content of the equation.
So there are two interesting questions. Vaibhav is asking, what would happen to the sun after its death? And Soham is asking, would the solar system be threatened when the sun dies?
Yes,
basically
yes.
asking about the death of the sun.
Yes, yes, that is the work of Chandrasekhar. In fact, sun will die as a white dwarf. It will become a very small object. There will be nothing actually to overcome the gravitational pull of the matter present in it. So therefore, it will just become a dwarf, and finally it would melt away, basically.
And what will happen to the solar system then?
Pardon? Oh, there will be no solar system. See, without sun, there is no solar system.
Yeah. Okay. So, sir, there is a question. I don't know his name.
We should not worry about it. That will take billions of years. So,
I think we have more pertinent worries of climate change right now.
That's right. That's right.
And thank you very much for mentioning the plantation that we did together. But it is thanks to you and your friends that the trees have really grown up, because planting is the easier part. Taking care and nurturing them is the more important part.
Yes, yes,
and
yes,
very often, I would like to tell you all, we talk about plantation drives, and we actually talk as if the plantation is the end in itself. Plantation is just the first step.
That's right.
You have to nurture, protect, give protection to the plants, and then ensure that there is proper nurturing and care.
I should just add, Sujit, here. Can I just add one line?
Yes, yes.
Yeah. Establishing educational institutions is also the first step. To make it grow and grow to real height is a tremendous effort. That is why, for example, Cambridge University, Oxford University, they have been growing since they were actually created over these 1,000 years. which we don't have patience. Actually, we seem to have we are losing patience with everything, like politics. So that's not the right way to groom educational institutions.
Exactly, absolutely. So there's this person who's asking, the underworld guy, he's asking if the mega project Dyson sphere, is it really possible?
What is it?
He's asking about the mega project Dyson sphere.
What is that? Dyson sphere, I don't know. What is it?
Okay, I also don't know. But anyway, we'll move on.
Okay.
We'll move on. So I think there's a young girl, Pratibha Rani. She's asking, what is the meaning of galaxy?
Oh, that's a good question. Just as the solar system has 8 planets, there were 9 planets, and now we call 8 planets and sun. So together they constitute a solar system. Similarly, there are billions of stars in a particular galaxy. And as I just explained, there is a center of galaxy at which a very compact supermassive black hole is sitting, whose mass is million times the mass of the sun. And around this center, all the stars are actually moving in orbits. For example, our sun is moving around this center of the galaxy, or the compact object which Professor Reinhard Genzel and Professor Andrea Ghez team have discovered. So, and the speed is around 240 kilometers per second. So it would take something like million years for the sun to actually make one orbit around the compact object, which is the center of our galaxy. So galaxy has something like 10 to the power 11, 12 stars. And the visible universe, which we have seen through our telescopes, has something like 10 to the power 11, 12 galaxies. So in all, we have actually something like Avogadro number of stars in the entire visible universe.
Right. So, for instance, Pratibha, I would also like to tell you that the word galaxy is also used as a metaphor. You know, in a non-scientific term, for example, if I talk about the galaxy of stars in Odisha, then I am talking about, you know, all the stars together. You know, basically we are talking about the intellectual stars there. So
that's right.
From a science, you know, it can be used in a general sense also. That way.
That time we borrow the word from astrophysics.
Yes. Sir, Swayamjit is asking, what is the name of the nearest black hole to Earth and the distance in astronomical units? The nearest black hole to Earth.
Obviously the one which this year's Nobel Prize has gone to, because this is our galaxy. So the supermassive black hole there is, if you talk of other black holes in the galaxy, I don't think we have been able to actually find, but there are many black holes actually spread everywhere. And since they are black holes, we don't get enough information from them. You have to actually be very confident to look at the black holes if you know where they are. But now we are sure that at every center of every galaxy, we have a black hole, a supermassive black hole. There are also other stars which are dying. And as I said, if the star mass, initial mass is more than the 20 solar mass or 30 solar mass, they would die as black holes. So there would be black holes spread all around, but which is the nearest? I cannot right now tell you, but you can always look up in
the one that was observed by Ghez and Genzel, was that in our galaxy?
That is the center of our galaxy.
Okay.
The picture that I showed of the galaxy. So they are now trying. You see, I gave you the picture, a direct picture of black hole. That was observed in another galaxy, M87 galaxy. But now they are trying to get similar picture for this particular compact object, which Reinhard Genzel and Andrea Ghez have discovered. That's the next attempt.
Okay. So Sangeeta is asking, you know, because you've been involved with education also of children, school education, in your opinion, how well are textbooks getting updated with these new discoveries happening? or do you see that as a major gap?
Well, about textbooks, in English medium or in Odia medium?
You can talk both. You can talk about both.
Okay. So what I find, the textbooks nowadays are little updated very fast, in fact, compared to what the people can really grasp. See, in 7th class, 8th class, we are now talking about chemical equation balancing, etc. And we are talking about atomic structure, which we read when we were in pre-universities. So sometimes I feel, even in literature also, they have some subjects or the essays or poems written by eminent poets and writers. And there are many, sort of 20, 25 of them in each year. I really don't know whether one would be able to do justice to that kind of thing. For example, I will give you one very important line, which I read just yesterday in Louis Gluck's poem, The Myth of Innocence. She has got Nobel Prize for Literature this year. In one poem, she writes, innocence cannot will knowledge. Innocence cannot will knowledge. So that means, what I understand, you may be able to tell better. So innocence never really invites knowledge, can never invite knowledge. So, sorry, not innocence, ignorance. I'm sorry. Ignorance never wills knowledge. So, you see, so why I'm saying this is because if I want to really make a student understand this line, then you have to really be at it and then convey the meaning. You cannot just say that ignorance doesn't will knowledge. You can't just say a sentence and then finish with it. So every line that a great writer writes has a lot of connotations which you have to actually drive home to the students. And what I see in direct answer to the question that you have asked, I would say that they are trying to sort of jam up all things. For example, today's talk, which I just gave, it's a very involved thing, extremely involved thing, because it's highly mathematical in one sphere. In theoretical sphere, it's highly mathematical. In the observational sphere, it's actually using the latest of the technology and the technique. So it's very difficult for a common man to really grasp what is really happening unless you bring it down to a level where some of the details are lost, but at least the spirit is conveyed. So that is what I think is more important. You don't have to really bother young students, particularly when they are in their schools, with a lot of details. I don't like that. You give them ideas, you give them concepts, and they on their own will grow.
I think that's a very important point sir has mentioned. Something I would like to mention here also, because that is a common thread. I talked about it, he talked about it, and the point is about curiosity. I think the important thing here is not to put a lot of information down their throats, but right. How can we stimulate their curiosity to learn? So, for example, I'm very happy that though we mentioned that this is for older children, there are some young children who listen to our storytelling who attended this because they were curious. It is okay. It is okay if I did not understand everything today, but at least I think what we should really appreciate is the curiosity to learn. We have a library, and sir, I'll tell you, I feel very sad when children say that our parents will allow us to go if you organize a competition.
That's right.
And if you're not organizing a competition, parents say, why are you wasting your time reading books? And sir will tell you, I have visited sir's house because his sons are my friends, and he reads a lot of literature. And in fact, I would like to tell everyone that there was this famous thing that Einstein said. I think apparently there was this conversation where a woman asked him, I want my son to be a scientist. What should I do? And Einstein had said, please read fairy tales to him. Then she said that I'm asking a serious question. Please don't joke. He said, I'm telling you that only. And if you want your child to be more intelligent, then read more fairy tales. Because, the creative imagination that Einstein talked about, and he said that is best, fostered if you listen to fairy tales, if you read fairy tales. So reading literature, the curiosity to explore a world beyond what you know. I think that is something that Sir is talking about. That instead of just forcing them, increasing the syllabus,
that's right.
increasing, and those things they will not remember. But anything that the child discovers out of curiosity, definitely the child will remember and understand that. I think we have passed way beyond. There are many questions still. I'll just see if maybe one last question. Sir, I would request you, what we can do is, I would request everyone to email your questions to Sir. If they have not been answered, you can email them to contact Bakul. I'll just repeat the email ID here. Yes, contactbakul@gmail.com. So if you email us your questions, I will send them over to Sir. And Sir, I would request you if you could answer some of them. And maybe you could put some questions together and make one document, and we can pass it on to everyone, whoever has emailed us the questions.
I will be happy to do that.
Thank you very much, Sir. So that is what we will do. And I think we will end now. It has been wonderful listening to Sir. And I love, what I really learned from him is the patience. That is a mark of a real scholar, not just a scientist. The patience with which he was, and the beautiful way in which he was trying to understand important concepts, to knowing that there are very young children here in the audience. We have had a very diverse audience. There have been, I think, serious scholars of physics and science, and there have been very small young children also. But I think I could see the request from Sir. Those of us who are listening to this, please, when we work with young people, let us try and foster their curiosity as much as possible, rather than, peddle them with a lot of information and ask them to parrot out information. I think that is something that, Sir, anything else, parting words you would like to say before we end today?
Let us learn and let learn. Let us live and let live. Let us grow and let grow. Thank you.
Thank you very much, Sir. It was lovely having you. And as I told you earlier, we'll be back every Tuesday at 7 p.m. on Facebook, YouTube, and Instagram to talk about the Nobel Prizes. And if you are interested in checking out the other online engagements that we are doing, the storytelling sessions happen every Saturday and Sunday. And the storytelling sessions are not just for small children, they are for children of all ages. So if the child in you is still alive, you would definitely love the sessions. So Saturday, it is in English, where we travel to different countries and try to know about their country and their culture. So for example, on Diwali, 14 November, Sir, you'll be happy to know, it is Children's Day. It is also Diwali that day. We are traveling to Indonesia that day to hear the Indonesian Ramayana. And it will be, our storyteller is actually Muslim, a Muslim storyteller from Indonesia. So similarly, we are traveling to different countries and trying to understand different cultures. So you can join us. And every Sunday at 9 p.m. again, we have Robibar Gapobar, which is like storytelling in Odia. So Sunday means story time. And of course, Tuesday back with the Nobel Prize in Economics next Tuesday with Professor Jeevan Rampal from IIM Ahmedabad. Thank you very much. See you, and do not forget to subscribe to our channel on YouTube and follow us on Facebook, Instagram. Thank you very much.
Thank you. It's a pleasure.
In education, that we are trying to promote reading. As statistics say, if 50% children in grade 5 cannot read the textbook of grade 2, then what is really happening? That's because the basic skills of reading and writing is not there. So we thought that if we have to change this cynicism, then we need to demonstrate what is possible with small contributions. So that is the idea basically that Bakul is trying to demonstrate, what is possible entirely with volunteerism, entirely with small little contributions. We asked people to contribute books to set up a public library in Bhubaneswar. and a children's library was set up in Bhubaneswar. And now that children's library has become a general library, a public library with more than 20,000 books. So that is one of the major things. Another major area of intervention is environment. A lot of environmental education, but through films and through creative methods. So we have a traveling film festival on environment. We go to schools, colleges, apartments and screen films on environment, primarily on climate change and on issues of water and sanitation, two issues that we're working in. And at the libraries also, we conduct a lot of workshops on creativity. You know, we all want the world to be a better place, and we have our own ideas of how it can be better. The thing is, can we all start in some small way towards addressing that? Can we say that in some small way, this world is the way I want it to be because I have done something about it?